Hi ladies, today we are going to start the quantum theory part of the notes. But before we start with the quantum theory, I just want to kind of go back over the Bohr model. Now remember, Bohr was a scientist who came up with the idea that electrons traveled in fixed paths around the nucleus and that each energy level had its own amount of energy associated with it, and the energy level closest to the nucleus had the lowest amount of energy. And as you move away from the nucleus, the amount of energy in each energy level gets greater and greater. Also remember that electrons have two states. They have ground states and they also have excited states. An electron is able to move from its ground state to its excited state by absorbing energy. When it absorbs enough energy, it can move to that excited state. Now remember, they don't stay in that excited state for very long because they're not very stable. So they're going to release the same amount of energy that they have absorbed. And when they release that amount of energy, they return back to their ground state, and we are able to see the released energy in some form of light. And that is what you guys observed while we were doing the flame test. Today we're going to look at the quantum theory, and from the quantum theory we are going to move to electron configuration, and then we're also going to look at orbital notation before we get into the periodic table and periodic table trends part of the notes. So we're going to take a look at the quantum model of the atom. A lot of times when people hear the word quantum, they kind of freak out a little bit. Quantum theory is just a simple way or a simple explanation that helps us to understand where the spectral lines come from, and it also describes the electronic structure of the atom. Basically, the quantum theory helps us to understand where the electrons are in an atom. Now, we're going to start with the Heisenberg uncertainty principle. The Heisenberg uncertainty principle was named after a German physicist by the name of Werner Heisenberg. The Heisenberg uncertainty principle states that the position and momentum of a moving object cannot simultaneously be measured and known exactly. Well, what does that mean? That means that we cannot know at any exact moment where an electron is and the speed that it's traveling. We can know one or the other, but we can't know both of them at the same time. At any given moment, a scientist knows probably about 90% sure of where an electron is. So only about 90% of the time can we actually know where an electron is. It's kind of like if you stare at a ceiling fan while it's on and you try to pinpoint where the blades are, and the minute you kind of fixate on a blade, it's already moving. It's kind of the same idea. Now, there's also a scientist known by the name of Schrödinger. In chemistry, we are not going to be doing any mathematical equations, but there is something called the Schrödinger's wave equation. And this equation was discovered again by a scientist by the name of Schrödinger. And with his wave equation, we can figure out two things. His wave equation showed us the electron's probable location. These locations are known as orbitals, and the motion of the electrons cover an area called the electron cloud. So, for instance, if this was our nucleus here, and these were our energy levels, the electron cloud would be the area that contains the cloud. Okay, all of those energy levels would be considered the cloud. Okay, and those electrons would be moving somewhere in that electron cloud. We only can figure it out about 90% of the time. The other 10%, it's just unknown. Now, Schrödinger's wave equation, in order to solve it, there are 4 parameters, 4 things that have to be known. And again, we're not going to be doing any mathematical equations, but we are going to discuss something called quantum numbers. And quantum numbers are basically 4 numbers that are used as kind of like an address for electrons. It's kind of like this. You have a house address. There's a number, there's a street address, there's a city, there's a state, there's a zip code, and we know that that's your home address, but we don't know exactly where you are in your house at every given moment. We know that there's a probable location that you might be in your room or you might be in the kitchen. Same with an electron. We can pinpoint the energy level, we can pinpoint the orbital, we can even pinpoint something called sublevels, but we're not exactly sure where they're going to be. So the 4 quantum numbers that we're going to be looking at are N, L, M, and S. The first quantum number is the easiest quantum number. It's called the principal quantum number, and it's represented by the letter N. The principal quantum number indicates the energy level the electron is in and the probable distance from that nucleus. The larger the number, the farther away from the nucleus. So if we have an electron in energy level 1 and an electron in energy level 7, then the electron in energy level 7 is farther away from the nucleus. Now, each principal energy level is composed of sublevels. So it's kind of like you have a house, and inside your house you have rooms. Well, we have energy levels, and inside those energy levels we have sublevels. Now, there are 7 main energy levels. N is equal to 1 is energy level 1, N is equal to 2 is energy level 2, N is equal to 3 is energy level 3, and so on and so forth. So that one's pretty easy. Sub-energy levels are represented by the letter L. The sub-energy level indicates the shape of the orbital an electron occupies. There are 4 possible shapes. So think of it again as your house. Inside your house you have these sublevels. Well, these sublevels, which are your rooms, have different shapes to them. Same thing here. Our energy levels have sub-energy levels, and it happens to be the shape. The S shape is a sphere shape. The P is a peanut shape, also known as a dumbbell shape. The D is a double peanut shape, and an F shape is a flower shape. It is the highest energy level. So let's take a look. So when we have an S-shaped orbital, it's basically circular. There is only one position for an S orbital. If you take a look, it's a round sphere. No matter which way you turn it, it looks the same. So there is one possible orientation. The p orbital, these are our peanut or our dumbbell shaped orbitals. There are 3 possible orientations. So again, if you take a peanut and you rotate it around an axis, you will get 3 different orientations. Orientation 1, orientation 2, orientation 3. The next shape, this is our d orbitals. These are our double peanut shapes. And again, we're going to have 5 possible orientations. Orientation 1, 2, 3, 4, and 5. Our next orbital shape is our F orbital. This is our flower-shaped orbital, and it has 7 possible orientations. 1, 2, 3, 4, 5, 6, and 7. So 7 orientations. So if we take a look, S has 1 orientation, P has 3 orientations, D has 5 orientations, and F has 7 orientations. S, P, D, and F 1, 3, 5, and 7. The next quantum number is the magnetic quantum number. The magnetic quantum number shows our orbital arrangement, how it's arranged in that space. Each sub-energy level may have the following number of arrangements. Again, S has 1 orbital arrangement, P has 3 orbital arrangements, D has 5 orbital arrangements, and F has 7 orbital arrangements. The next quantum number, this is our spin quantum number. It is represented by the letter S. The spin quantum number indicates the spin of an electron. An electron spins either clockwise or counterclockwise. Each orbital, so our orbitals again, are S, P, D, and F. Each orbital can hold 2 electrons. One of the electrons spins clockwise and the other one spins counterclockwise. Well, some of you might be wondering, why do they have opposite spins? Well, they have opposite spins because all electrons are negative and they repel one another. This repulsion results in opposite spins. So, what we've done is we've talked about different energy levels. And I know this probably isn't making much sense, but I promise it will when we get to electron configuration. Remember, there are 7 energy levels. Energy level 1, so N is equal to 1 is energy level 1, N is equal to 2 is energy level 2, N is equal to 3 is energy level 3, and so on and so forth. Each energy level has sublevels. So for instance, energy level 1, since it is the smallest energy level, it can only hold a certain amount of sublevels. As we move away from the nucleus, so energy level 1 on out, the sublevels for each energy level are going to increase. And the reason that they increase is because there is more room the further away from the nucleus we move. Which makes sense if you think back to your Bohr diagrams in physical science. The ones that you did with the little dots, and as you moved away from the nucleus, you had more and more electrons. Well, the reason you can have more and more electrons is because the energy levels are bigger and there's more room there. So, if we take a look at this and we kind of put it all together, N is equal to 1, that's our first energy level. It can only hold an s orbital. N is equal to 2 is our second energy level. And this energy level holds an s orbital. Oops, let's go back and redo that. Holds an s orbital and 3 p orbitals, because remember, there are 3 orientations for a p orbital. Energy level 3 holds an s, a p, and 5 d orbitals. Why? Because there is more room. Well, energy level 4, so N is equal to 4 through 7, they all look the same. They can each hold S, P, D, and F. And F has 7 orbitals. Now, what I want you to remember is that in each orbital, 2 electrons can exist. It doesn't mean that they always exist, but they can exist. So, if we kind of take a look at our energy levels can have 1 or more of the following sublevels. We have 1 orientation of our S sublevel. It can hold 2 electrons. Well, there are 3 orientations of our peanut shape. Well, if each one can hold 2, 3 times 2 gives you 6 total electrons. Our D sublevel, Well, there are 5 orientations of D. Well, if each one of those can hold 2 electrons, there is a total of 10 electrons that can be held there. Our F sublevel has 7 orientations. Each one of those orientations can hold 2 electrons. 7 times 2 gives you a total of 14 possible electrons. We're going to be talking about something called valence electrons. Valence electrons are the electrons in the outermost energy level of an atom. Valence electrons are the electrons that are used during chemical bonding. Over the next couple of days, we are going to be looking at electron configuration and orbital notation. And by looking at these configurations and notations, you can tell how many valence electrons an atom has in order to bond. So we're going to stop here because the next thing we're going to get into is electron configuration. So what I would like you to do is pause the video, and then I would like you to go to Moodle and open up the quantum mechanics worksheet. And basically the worksheet is kind of a review of just the 4 spin number. So go to Moodle, open up the worksheet. When you open up the worksheet, it says quantum mechanics and electron configuration. And basically it's putting everything that was in that section of the PowerPoint into chart formation. So if we look at our first column, it says principal quantum number. Principal quantum number is represented by the letter N. Now what I want you to remember, here it's list 4. Principal quantum number 1, 2, 3, and 4. Okay? Now remember there are 7 energy levels. So 4 through 7 are arranged identically. What I'd like for you to do is, using the PowerPoint that is also posted on Moodle, I would like for you to fill in each one of these sections. So the next column says sublevels in main energy level, number of orbitals, then number of electrons per sublevel, and then number of electrons per main energy level. So for instance, in the second column, sublevels in the main energy level. Well, energy level 1 has an S sublevel, energy level 2, S and P, energy level 3, S, P, D, and F, S, P, and D. Energy levels 4 through 7, S, P, D, and F. From there, you can go ahead and fill in the number of orbitals. That's going to be the orientations, and then the number of electrons per sublevel, and then try to figure out the number of electrons per main energy level. Once you are done with that, you can go ahead and submit that to Moodle.